Swayam Prabha. Digital India. Educated India.
Hello everyone, welcome back. In the last lecture we were talking about optical properties of materials. We looked at the Lorentz model, which describes the optical properties of dielectrics quite well. And then we also introduced the Drude-Lorentz model, which talks about the optical properties of metals. So in this lecture we would like to discuss a very fundamental relation that is known as Kramers-Kronig relation. The reason this is important is, if you look at the models that we have seen so far, okay, you would have noticed that, for example, in the Lorentz model here, there is an absorption, strong absorption at the characteristic wavelength, frequency, right? Whenever you have such strong absorption, you have an associated change in the real part, okay? So, always strong absorption is accompanied by strong change in epsilon. In this case, if I'm talking about refractive index, n of omega, refractive index. Okay, this is something that even we see it in other places. For example, in the optical properties of metals, you see that for gold there is a strong absorption at the about 2.4 EV, the interband absorption we talked about. So whenever you have such strong absorption, in the real part you see that the model and the experiment doesn't quite agree. Okay. Similarly, for case of aluminum, you see a variation in the model and the experiment in the lower energies, and you see, sure enough, there is a mismatch even in the imaginary parts. Okay. So it seems like there is a strong relation. And why is this happening? Why is this relation coming about? Okay. So the reason for this is what is known as causality. Causality simply means that effect cannot precede the cause, or the stimulus cannot precede the stimulus, right? The reason, an example for this would be, let's say you're trying to fill water into a tank, okay, using a motor. So you connect a pipe, and whenever you turn on the motor, you turn on the power, then the water starts flowing and then the tank starts getting filled up. Can the water start flowing in the pipes without switching on the motor? It cannot, right? So the stimulus is the switching on the motor, and the effect is that it will flow through the pipe. Even after you switch off pipe, it might actually flow for a short while. Okay, but it cannot happen that before you switch on the motor, the water can flow. Okay, you can think of many such examples. For example, somebody just hits me. Okay, I'm not going to feel the pain before the actual contact is made, right? So this sort of a thing is known as causality. Okay, and why is this important in our context? Well, it is important because we are essentially applying electric field. We are applying electric field, right? That is my the stimulus. So if I apply electric field, what happens? The effect is basically polarization. Can the polarization happen before the electric field is applied? Okay. Well, that cannot happen. Okay, that violates the fundamental laws of time, right? Time always propagates forward. It doesn't propagate backward. Okay. So essentially what we are trying to say mathematically is, we are asking the question, if we talk of polarization at a time t, can this be expressed as epsilon naught chi of t E of t? Okay. So the question is this correct? Okay. By now, it should be obvious that it is not correct. The reason is, this chi of t I can define using an oscillator, right? And my oscillator, we already saw any Lorentz oscillator, if you take, the spring mass system can actually respond with a phase lag. Okay, can respond with a phase lag. What does it mean? It just means that it's not instantaneous. That's it. Okay. So what? Well, this has very strong implications. Okay. So yeah, we already talked about it. This is incorrect. This is incorrect. So now what should happen is the polarization at a particular time t, in fact, depends on the electric field and the impulse response at some time in the past. Okay. For example, if I plot out the impulse response function, it should look something like this. What it means is that the chi as a function of time should be 0 before the signal is applied or stimulus is applied. After that, it can go on for some time. It cannot be that you have a impulse response even before this. This is an incorrect response. Okay, it cannot happen. So what we are saying is, if electric field is equal to 0 for t less than 0, then the polarization has to be 0 for t less than 0. That's a important thing. Okay, and at any point later about t equal to 0 can be calculated using this equation. Okay, so now if this is, you can immediately recognize it's simple convolution. So my polarization in the time domain, it cannot be a simple expression, it's a sum or an integral. But in the frequency domain, it's simple multiplication. Epsilon naught chi of omega E of omega. Okay, if I convert my electric field into frequency domain and multiply it with the susceptibility, I'll get my polarization in the frequency domain. Okay. So, based on just this basic idea of causality, I can actually use residue theorem, Cauchy's residue theorem, and there is in the textbooks, if you'll see that there's a rigorous proof that is given for this. And finally, at the end of it, they come to two equations, which are known as Kramers-Kronig relations. And those are shown here. The essential idea that I want to communicate right now is, whenever I have a, let's say imaginary part of susceptibility, if I know that, I can calculate directly the real part of susceptibility. Similarly, if I know the real part of susceptibility, I can calculate the imaginary part. Okay, there is this integral that has to be performed. That's it. Okay. So now, once we know susceptibility, we can immediately calculate what is epsilon, because epsilon is simply 1 plus susceptibility. That is even true in the frequency domain. All right. So we won't really get into the numeric or the rigorous mathematical proof of this, but I'll try to give you a very abstract or intuitive picture using Fourier transforms, why it should be so. Okay. So the idea is that if you, let's say, have a causal impulse response of this fashion, I will actually do some small tricks and try to convince you that actually it can be represented, there should be a relation between real and imaginary parts. Okay. The way we do that is, let's say this is psi of t, which is my impulse response, chi of t, is basically 0 for t less than 0 and is equal to some h of t for t greater than 0. Okay. I'm just assuming that. Okay. It can be any function. Okay. It need not be a proper sinusoidal oscillation like this. It can be any complex function. There's no harm. Okay. Now, once I have a impulse response like this, I'll apply a trick from Fourier theory. Okay. What I'll do is, I'll write it as a sum of h of t. I'll write it as a sum of h of even function and an odd function. Okay. The basic theory of functions tells me that any function can be written as this sort of a sum. I can construct this sort of a functions, two functions, odd and even functions, which will satisfy. And pictorially I have shown this here. Let's say you have my initial psi of t like this, chi of t. Now I can think of a odd function. Oh, okay, this actually should be not even. This should be chi of odd. I'm sorry, this is mislabeled. This is chi of even. Okay. What we're trying to say is, let's say you have this. For t greater than 0, just replicate the same function. But for t less than 0, just take a minus of that, minus h of t, and invert it. Okay. So you can get an odd function of this form. Okay. Similarly, I can take a mirror image. Just take the same thing and just invert it on the time. Then you will get my even function like this. So now if I add my odd and even functions, what happens? Well, I should actually do, in this case, I have to basically divide by 2 as well, because I'm taking this chi of t, right? Odd and even divide by 2. I'll take an average. In this case, I can even write like this, half of that. Okay. So now on the greater than 0 side, exactly same function twice, add up 2 times h of t. On the less than 0 side, they are exactly opposite, so they subtract to 0. So you get h of t. Okay. So exactly same thing I'm doing. And why am I doing this? The reason we are doing that is, we know from our Fourier transform theory that the even function has a Fourier transform which is real. Okay. And the odd function will have a Fourier transform which is imaginary. So what? Well, now what we are trying to get to is, we are trying to show that these two Fourier transforms are related. And how are they related? Well, they are related because my even function here, h of even, right? H even of t, it is essentially the same function but with a multiplication of a signum function. Signum of t times h of odd. Right? So what we are doing is, signum function essentially is this, wherein you have t equal to 0 and this is 1, this is minus 1. Right? So what we are doing is, we are multiplying on the positive side, we are essentially multiplying it by 1, so nothing changes. On the negative side, we are multiplying by minus 1. So the even function is essentially take the odd function and then multiply by minus 1. So you get the even function. So this is true, right? Yeah, signum is essentially something that is equal to 1 for t greater than 1, t greater than 0, minus 1 for t less than 0, right? Now, so what? Now, I can go back and I can say that my h of t is simply signum of t times h odd of t plus h odd of t. Okay. So now we already know, of course, that this basically this Fourier transform ft is real, because overall we are multiplying with a minus. So overall the whole thing is still even function. Okay, it cannot be an odd function, so it's an even function. The ft is real, and in this case the Fourier transform is imaginary. Okay, and the both depend on the same function. Of course, there's a signum function, so there's going to be some variation, but they both depend on h odd of t. So real and imaginary parts are related. All right. How are they specifically related? Well, I mean, you can quickly see if I go into the frequency domain. This was a time domain expression here. This is a time domain expression. I'll go into the frequency domain. So if I go into the frequency domain, what I'll end up getting is h of omega is going to be signum of omega convoluted with h odd of omega plus h odd of omega. Okay, because I'm taking a Fourier transform essentially, then you have to delay it and all that, right? So essentially you get this. So I mean, what exactly this means is, you already know this. So basically this is simply minus infinity to infinity, let's say, signum of omega minus omega prime h odd of omega prime d omega prime. So convolution, I'm just writing it out. All right. Now, why is this interesting? Because if you look at this, this is a purely imaginary term, and this one is an interesting thing. The way we can understand is, we know that signum of omega minus omega prime is going to be 2 by j omega minus omega prime. Okay. So once it actually exhibits a functional dependence of, let's say around the omega prime, it's going to be, if you have this axis, it's going to be something like this, down, going to blow up at omega prime. Okay. Now what we are doing is, let's say we have an imaginary part of refractive index. Okay. I have my peak here, which is imaginary part. Now I'll apply, if I have a peak of this form, imaginary part, I'll start applying my, signum in the frequency domain. So it's going to be something like this. It's going to be something like this, and you move it across. As you move across, you'll start seeing that your real part, this is essentially the real part, right? The real part is going to be of this form, where it peaks, comes down and goes back up. Okay, so there's a very nice GIF you'll see in this web page. You can go and take a look. But essentially, that's what I'm conveying here. Essentially saying that as I move my signum in the frequency domain, initially my area under the curve increases, then it starts reducing, then again it goes into the negative territory and then goes back up. You'll clearly see this in this animation. So I've taken a couple of examples. So wherein if you're far away from the, let's say above the peak, then you see the contribution is mainly coming from the negative part. And as you move, the negative contribution reduces. In this case, the contribution is positive and it's increasing. Beyond a point, it starts reducing again. Okay. So this is the proof that the Kramers-Kronig relation is valid. Okay. So why is this important? I said this is very fundamental. The reason this is important is in many times, in many cases, we cannot measure both real and imaginary parts simultaneously. It's impossible to measure that. For example, if I want to measure absorption through refractive index of a material, okay, a block like this, how will we measure refractive index? Refractive index is essentially the amount by which the speed of light is reducing. There's no way we can measure speed of light easily, right? In a simple experiment at different frequencies, at different wavelengths and so on. So what we will do is, we will send a light beam with various wavelengths and I'll try to measure the absorption. Okay, how much light is getting absorbed. How will I measure the absorption? Well, I know the relation R plus T plus A equal to 1. So I'll measure my R and I'll measure T and I'll calculate absorption as 1 minus R minus T. So the reflectance and transmission I'll measure rather, and I'll calculate the absorption. Okay. So what if you measure absorption? Well, once we measure absorption peak, you can calculate what is the refractive index. You don't need to measure refractive index. Measuring, the delay at high speeds is very, very hard. Okay. I mean, no electronics can do that, right? So this is an indirect way of finding out. And also sometimes what happens is we will, in the next part of the lecture, I will talk about engineered materials, or how you can actually change the optical response. In those scenarios, you will not be able to find the response at all wavelengths or all frequencies. You'll only find the response sometimes in a narrow band of frequencies, but still it has to be Kramers-Kronig consistent. If it is not Kramers-Kronig consistent, then the device or the response is not what you think it is. Okay. So I see many times, I've seen PhD dissertations where they try to measure this, they try to measure the metamaterials absorption, and they'll calculate the real part, but then there is no relation. They don't verify that the relation is right. Okay. So it's an important part that you should be aware of. All right. So this holds true, and this cannot be violated for any material. It's just, it might happen that you're far away from the absorption, so there is not much of dispersion. By the way, the dispersion is basically refractive index changing with frequency, right? So when there is no dispersion, that means it's flat. Okay. So you can have this scenario, but this is something that you need to be careful. So we'll try to put in some example in this direction for you. So what we're planning to do is we'll open up a GitHub repository, publicly available. We'll have some of these examples given to you so that you can learn from that. Okay, in case you need them, you can actually try to learn from that. All right. So yeah, thank you so much for your attention. We'll see you in the next lecture. Take care. Bye.